Good morning. Thank you for connecting. So my name is Quisbert-Trujillo. I am the director of Nanoelec, and today we are welcoming in our webinar Ernesto Quisbert-Trujillo, who is a young scientist that has worked on IoT devices and their impact in terms of sustainability. The work was, a recent paper was published by him related to what we are addressing in the field of a program at Nanoelec related to human capital and training design. So Ernesto will present this paper. We will welcome questions at the end of his 30 minutes presentation. What I would like also to highlight is that this work not only is of great interest for the training design activities at Nanoelec, but also for some of our program, because of our industrial partners, whether they are in the field of microelectronics itself or system integration, in the field of energy infrastructure and buildings, are increasingly interested in assessing the impact of microelectronics at the system level in terms of power consumption, impact of storing data, and so on. So in 1 minute, I will let Ernesto start his presentation. In terms of organization, if you want to send questions, you can select a small icon at the bottom right of the screen. Can you show where it is? So here, in the chat area. And if you have any difficulty with the webinar interface, you can see or follow the webinar on YouTube on the channel Nanoelec. Just to finish, Ernesto now is working in a laboratory called G-Scop here in Grenoble. It's a laboratory that is specialized in the evolution of industrial systems and their organization, with know-how in co-design of process product, in optimization, and so he will introduce what he's doing. The presentation will be related to the impact of IoT devices and related services and their measurements of impact in terms of consumption. Thank you very much, and Ernesto, it's up to you. Thank you for coming. Thank you very much for being there.
Okay, thank you, for this invitation and for this opportunity to present my work. I would like to begin with an introduction of the Internet of Things. Next slide. Just have to click here. Okay. The Internet of Things is a technology composed of sensors and actuators that are installed in common objects and connect to internet and remote servers by gateways. The idea is to facilitate communication, human-to-human communication, or human to machine, or machine-to-machine communications to automate processes. This is known as a complete IoT system. An example is home automatization, an application of the Internet of Things to automate everyday tasks such as garden watering or monitoring water consumption. Along home automatization, there are numerous applications of the Internet of Things in healthcare, sport, entertainment, and more. Thus, the Internet of Things is present in the economic, social, and environmental development of our countries. A report from the International Economic Forum shows that in 2018, more than 600 IoT projects were launched in Europe. More of them, 70% of this project accelerated the development of innovation and industry and infrastructure, the development of more sustainable cities and communities, the access to clean energy, the well-being and the healthcare, and the responsible production and consumption. These and other projects have promoted the growth of the Internet systems and IoT systems in recent decades. A report from the research servers of the Congress of the United States shows that the number of connected IoT devices in 2020 was more than 9 billion, while in 2025, this number is projected to exceed 21 billion. Given this spectacular growth, some researchers have begun to inquire about the long-term environmental impact of the Internet of Things. But this is not easy because it requires to take into account a lot of factors. However, while the impact of producing IoT devices can be understood in terms of materials and energy used in production, the impact of using IoT systems, and specifically in the use phase, can be understood in terms of the total energy required by an application. So, for example, some researchers estimate the electricity demand of more than 300 terawatts hour for 2030 to cover mainly the operations of IoT servers in the industrial sector. This may seem like a lot, but it represents only 6% of increase in total energy consumption of data centers between 2010 and 2018. If the electricity consumption is efficient today, it's because data processing and cooling are efficient. However, considering the significant growth of the Internet of Things, the significant amount of data they generate, and especially the decline of the Moore's law, researchers are more prudent and project also significant growth in the electrical needs of IoT systems, reaching over 700 terawatts hour by 2030. By taking this into account, I become interested in investigating the specific impact of using a particular IoT system, with the purpose of developing a methodology for estimating and reducing this impact. Now, measuring and reducing the overall impact of using IoT system means measuring the amount of energy during a service. For local devices, this will be the number of batteries and the electricity consumption in a certain period. And for remote devices would be the electricity consumption over a certain period of time. While the electricity consumption and batteries of local devices is measured in function of time, the electricity consumption of the Internet and the remote servers are measured in function of the amount of data they generate. Now, with this in mind, I set out to measure the overall impact of an IoT water consumption monitoring system. This system is composed of an inductive pulse emitter and a flow meter. The former generates electrical pulses, which are interpreted as water consumption by the later. This system also includes a gateway that connects to Internet and a server which is accessible by a smartphone. Now, if we consider the service monitoring the water consumption of a square kilometer every hour for 2 years, according to the technical specifications of the system, the reference flow, that is the electricity and the number of batteries required by the system, would be as follows. 1 battery for the inductive pulse emitter, 1 battery for the flow meter, 105 kilowatts hour for the gateway, and 1 kilowatt hour for the mobile phone. But what is the electricity consumption of the internet and remote server? To answer this question, we need to determine how much data is generated during a service. So we made the following. First, we intercepted the data sent from the gateway to the server for 10 hours. Second, we estimated the data flow over 2 years. And third, we calculated the amount of electricity needs to process this data on the internet and in the remote server. And in this sense, with over more than 4 gigabytes generated along 2 years, the electricity consumption of the internet and the server amounts to 1 kilowatt hour approximately. And the total impact of this system rises to over 6 kilograms of dioxide carbon. You can see that the results show the significant contribution of the gateway to the impact. So the next question is, can we reduce the impact of this device? Or in other words, can we eco-design this device? Perhaps the most direct solution is to design an energy harvesting version of this dispositive. But to achieve this, the next question that would arise is, what is the workload of this device? Now, given that this device is only responsible for receiving data, the data from the application and retransmit it to the internet, a logical question would be, what is the transmission activity of this device? I investigate this and I confirm intensive activity for a service as simple as monitoring household water consumption. Indeed, a more detailed analysis shows that this system generates a lot of data. First, the system generates a lot of TCP traffic. TCP is a connection-oriented protocol. It generates a minimum of 4 acknowledged messages for each transmission. Now, in our system, the gateway transmits to the server every seconds to update the water consumption, meaning generating 4 TCP messages every 18 seconds. Now, from the point of view of the designers, this can be improved by adopting simple transmission protocols. This wouldn't guarantee the transmission of every message, but given their high frequency, it wouldn't be a problem. Now, the system generates also a lot of DNS traffic. DNS is an identification protocol. It asks the internet for the IP address of a server whenever communications are established for the first time. In our system, the gateway doesn't keep in mind or keep in memory the server's IP address. Instead, it asks to the internet every 18 seconds. Now, from the point of view of the design, this can be solved by modifying the gateway's program, and more precisely, by modifying the program of the memory. Now, finally, the system generates a lot of HTTP traffic during water consumption. This is because connections are not closed and the gateway sends an additional unplanned closing message. This can be solved in communication design for the user to the server. Now, to reach to these conclusions, we had to modify the system and apply an exhaustive data traffic analysis. So, is there exists another way to calculate the data flow of an IoT system in a simple manner? Now, this question is very important because it will determine the design or the redesign of local devices, as we will see in the next minutes. But for answer that question, I developed a simple approach based on an abstraction of the data flow of an IoT system. Indeed, the data flow can be represented by specific functions, such as storing, processing, or transmitting information. These specific functions are linked to electronic components that with determined capabilities and which constitute specific devices in specific layers: a sensor layer, an edge layer, and a cloud layer. By using this model, we can determine the theoretical data flow based on scenarios and capabilities of certain electronic components. For example, to determine the amount of data transmitted from the gateway to the server, we can consider first the electronic component of the gateway responsible for data transmission. In our case, a Wi-Fi module. Second, the minimum message size with the HTTP protocol that this component would use. Third, an optimistic scenario based on technical information with a transmission frequency of 15 minutes for system updates and another transmission frequency of 1 hour for user water consumption queries. In this manner, the data flow obtained theoretically is less than 1 gigabyte over 2 years, and the total impact calculated theoretically is just over 5 kilograms of dioxide carbon, which is 12% lower than the previous impact calculated empirically. Now, at the first glance, this method has its limitations and relies on certain assumptions. For example, in our case, we didn't account for additional traffic from communication protocols. However, the method is practical and helps determine the amount of data generated and energy required by local devices, as we will see. For example, by considering the component of the flow meter that transmits to the gateway, a LoRa module, and also considering the current consumption of this component in its transmitting and standby states, we can determine the following. First, the battery depletion in the transmitting and standby states based on message transmission time. Second, the battery lifetime in relation to the number and size of message transmitted by this component. So considering a scenario of 57 bytes size message transmitted more than 350,000 times in 2 years, we can say that at the distance of 2 kilometers with a transmission bandwidth of 125 kHz, the battery's lifetime of the flow meter is about 6 years. However, at a minimal distance of 14 kilometers under the same conditions, the battery's lifetime is only about 4 months. At this point, you may wonder, why is the distance determinant in my analysis? Because LoRa technology manages the quality of transmissions based on the distance between the two transceivers. To explain this, let's take an analogy. Imagine 2 people alone talking together in a park. Because the distance between them is short and there is no interference, it's not necessary to make much effort to communicate. However, as the distance between them increases and due to interference, communication gets worse and both people need to make more effort to talk. Making more effort means spending more energy. The person speaking must raise his voice and speak more slowly, while the person listening must pay more attention. In the same sense, As the distance between the two LoRa transceivers increase, the communication protocol causes the transmitter to send message more slowly, and the receiver to increase its reception sensitivity. Now, sending LoRa message more slowly means reducing the transmission speed and prolonging the time the transmitting state are activated, causing energy expenditure. In this way, the transmission capabilities of this component based on the distance, along with the amount of data to be transmitted within a certain period of time, both are important in determining the number of batteries and the impact of this device in its use phase. Concretely, by knowing the number of batteries required according to the distance, a designer can suggest the following recommendations for the eco-design of this device. Firstly, replacing the battery-based design of this component with an energy harvesting design would only be beneficial in a specific context. Indeed, if the transmission distance is approximately 14 kilometers, switching to an energy harvesting version of the flow meter would avoid continuous battery replacements in the short term, approximately 6 batteries every 2 years. However, if local transmissions involve the distance range of 2 or 4 kilometers, a self-powered design would only bring marginal benefits. That is, avoiding a battery replacement approximately every 6 or 3 years. What is worse, impacts could be transferred from the usage phase of this device to its manufacturing phase, depending on the complexity of the energy harvesting design. Secondly, maximum benefits could be obtained by using a transmission speed of 11 kbits in a bandwidth of 250 kHz. A battery would be replaced approximately once every 11 years. Additional to this analysis, the joint analysis of the LoRa components of the flow meter and the gateway both are very interesting too. Indeed, according to the manufacturer's specification, a gateway should not be installed more than 800 meters away from the flow meter. This would mean adding 2 more gateways if we wanted to monitor the water consumption on an area of approximately 2.5 kilometers square. Although determining the reasons for these recommendations is beyond my scope, I believe the manufacturer aims to maintain high-quality transmissions between the gateway and the flow meter. However, this may not necessarily be the case. Under the assumption that message of 57 bytes are perfectly managed by a gateway in a bandwidth of 125 kHz, it's very probable that under the same conditions, a flow meter could be perfectly managed by one gateway within a range of 2 kilometers and for more than 5 years, as my estimations suggest. All these aspects help me formulate the following eco-design guidelines for similar IoT systems. First, when designing or redesigning IoT systems, it's very important to consider both the operational time of local devices and the energy consumption patterns in various circumstances. This includes taking into account the capabilities of electronic components in relation to data process functions, such as sample rates, maximum payloads, transmission speeds, bandwidths, and transmission range. Second, designers should analyze in detail the functions and capabilities of electronic components to propose reasonable designs. or identify technical features that promote or challenge design. For example, in our case study, using FSK modulation is not suitable for LoRa transmissions due to the simplicity of data the sensor generates. That is, only interpretations of electrical pulses. Third, designers should consider the transmission frequency and size of transmissions between devices when modeling the data flow of a system. In particular, additional data flow must be considered when users and devices retrieve information from remote servers. Fourth, when an application shows consistent behavior, such as in our case, with constant water consumption, it's possible to predict information from historical data on servers, thus avoiding massive updates from local devices. And finally, for high-frequency transmissions in IoT systems, it's suggested to employ connectionless protocols and reinforce security. However, it's very important to consider the increase of energy consumption due to security routines. In conclusion, the Internet of Things is a technology composed of local and remote devices that conform systems. These systems have increased significantly in recent years, bringing many benefits to our societies. However, the environmental impact of the Internet of Things is real and could be very significant in the coming years, especially in the use phase. With this in mind, I set out to measure the concrete impact of using a system, and then to think about a simplified method of calculating and reducing impact. This method is an abstraction of the data flow of an IoT system, built from basic functions and capabilities of electronic components. The method proved promising, especially for the eco-design of local devices. As an example, we use this method to analyze the impact of a device in terms of battery depletion and based on certain capabilities, that is, the current consumption in two transmission states. Our method also highlighted a very interesting point of discussion regarding the number of gateways needed for an extended IoT system. And at the end, I share with you some eco-design guidelines based on my research in this article. I hope that these guidelines and the method I propose are useful for your own projects. And of course, I would be happy to answer any question you may have. Thank you very much.
Thank you very much, Ernesto. Very interesting. Are there any questions that have been integrated into the presentation on the platform? Maybe I can ask a first question to initiate the discussion. When we exchange to prepare, and when I saw some of your presentation, so what I understood is one of the originality of your work is based on the fact that you are analyzing the system from a service point of view, and not only in terms of architecture and hardware components. Can you maybe highlight what was specific in terms of methodology and concept, analyzing a service rather than a hardware system or a system?
Okay. So when we tried to understand the impact of the Internet of Things, we needed to think about what is the purpose of an IoT system. And from an essential point of view, is the transformation of information from data, raw data, to information that would be used for machines or for humans. So in that case, we don't think about a product such as a sensor component, but we think about the system that collects this data and transforms this data into information.
Okay, thank you.
There's a question.
So there is a first question. Did you leverage manufacturing impact also of the system itself?
Okay. The focus of this article is measuring the impact of an IoT system in the use phase. Manufacturing phase needs another kind of reflection that involves an abstraction of the specific characteristics that helps to measure an impact. I talk about physical characteristics, for example, the quantity of certain materials, technical characteristics, such as that characteristic of transmission parameters, and also circular characteristics. It is possible, for example, separate electronic components for further recycling process. So the method that we propose in this article is oriented to the use phase and must be plugged with another method that I propose in another article that focus on the hardware part, and together conforms a very global methodology for impact estimation and reduction.
Okay, so Philippe has another question concerning the integrating the perspective from the benefit of the monitoring in your...
Okay, in fact, this is a very interesting point of discussion, because we tried to understand the cost benefits in global terms. What is the benefit, the global benefit of water consumption? Of course, we need to integrate this aspect in the analysis. Unfortunately, in the work that was done in my article, we focus only in the impact estimation and reduction of the servers, but not about the benefits of these servers, or the global cost benefits of the system. But it's very challenging because we need to think about a method estimation of the benefits and impacts for the economical part, the environmental part, and also the social part.
Okay, thank you very much. I have another question concerning the scaling up of such studies on very complex systems. We start within Nanoelec program looking at systems that are monitoring buildings. So that means that we have hundreds, maybe thousands of devices connected, choices of architecture in terms of storage, transferring data. Have you given some thought on how to scale up your methodology to much more complex systems?
We can use this method to understand the impact, and from that try to estimate the potential impact of a more big system. But what we need to take into account is making an abstraction of how the system behaves along the time, and try to understand the specific characteristics that expose data, for example, and try to adapt this kind of reflection, or the results of this reflection, to a more extended system. In the case, for example, in the article, we saw that when we want to measure the water consumption of a more extended terrain, according to the manufacturer, we need to extend the number of gateways. But this recommendation is because I believe that the manufacturer wants to guarantee high quality of transmissions. So if we want to guarantee the quality of transmissions, we need to see what happens in the data flow of the system.
Okay, thank you. Another question concerning did you study the messaging system itself in terms of protocol? The question from Karim is, you would imagine a very short message for such monitoring system. So did you give them some thoughts on, or did you work on that?
Yeah, absolutely. Within the analysis of this system, we saw that we have a very intensive data traffic activity. That is not necessarily the case because it's a simple application of monitoring water consumption of a home. So the application and the IoT system itself is over designed. We can say that because we have a lot of frequency that is not necessary, of transmission frequency that is not necessary. So yes, maybe we need to think about simplify the data transmissions between the gateway and the cloud server, but also think about simplify the communication means. That is because at the end of my presentation, one of the recommendations was thinking about more transmissions with more simple protocols. But we have also to think about what is the consequence of taking into account more simple protocols related to the security and the transmission quality of the system, of the message.
Okay, thank you very much. Another question from Vivian concerning the impact of the security protocols in terms of concern. You mentioned that at the end of your presentation, mentioning that adding security is necessarily power consuming. Have you read a biography or a bibliography, or have you worked a little bit on that part of what is the impact in terms of energy consumption of integrating security into the system?
Yeah, unfortunately, I didn't see the direct impact of applying security, but I could say that from the point of view of impact estimation, but from the point of view of design, there is actually very interesting approaches about replacing, reallocate the security either to the local site or either to the cloud site. I think that both approaches are very interesting from the point of view of the placing or the energy loads to the local site. We see, for example, the federating computing, in which we can apply security routines in microcontrollers, and also security from the point of view of cloud servers. But we have a double work. First, we need to think about simplification of from the software point of view, and simplification from the hardware point of view for applying these security routines.
Okay, thank you. I think Karim had another question concerning the protocol, asking whether a pull system, rather a push one, would induce a reduced energy consumption. So in terms of the way that you design the system. So I guess a pull system is that the gateway requests information when it needs it. Maybe, I don't know.
Yeah, it's interesting aspect that I saw in the data traffic analysis in my work is that whenever the user wants to see his or her water consumption, the gateway retrieves information to the cloud server, but also the cloud server retrieves information from the local system. Now, unfortunately, we can see what we have inside this message, but I could say that there exists a kind of data accumulation from the gateway, and also whenever the user retrieves information about water consumption, this accumulated data travel to the cloud server. So in the case of this case study, we have both a pull system and a push system. But unfortunately, we can see what is the content of this message. I believe that is a kind of the system, the cloud server retrieves also information, but about data. It retrieves data about administration of the system.
Okay, no other question for the moment. So maybe we can conclude. It's almost 10 o'clock. What we may mention is that there will be a replay available for that presentations. If you want to go back to the slide that have been presented by Ernesto. We have another seminar on Friday. It's the day of the celebration of the International Day for Women, and so we will be animating a roundtable with women involved with responsibility jobs in the industry, and it will also be available on the webinar platform, on our webinar platform. So thank you.
It will be in French.
And it will be in French this time. So thank you, everybody, for joining us, and we hope to see you the next time we have an organization. Thank you again, Ernesto, for your presentation, and François for the organization.
Thank you very much.